Hi, I'm Gianluca and welcome to this new video on practical statistics for data analysis. Today we're going to talk about Chebyshev's inequality, a simple, underrated tool that becomes incredibly powerful when your data looks like the messy chart you see on the screen, skewed, irregular, definitely not a nice bell curve. Chebyshev's inequality steps in exactly here. It gives you hard, guaranteed bounds based only on the mean and standard deviation, without assuming any specific shape for the distribution. By the end of this video, you'll know how to use Chebyshev's inequality to estimate variability, detect potential outliers, and set robust, conservative bounds on your data and model errors, even when normality is a bad assumption. Let's look at what typically happens with real data. In textbooks, we often see a nice symmetric bell-shaped curve, and we learn the famous 6-8-9-5-9-9 7 rule for how much data falls within 1, 2, or 3 standard deviations. But in practice, whether you're working in business analytics, finance, or machine learning, your data usually looks more like the small charts on this slide. You get skewed distributions where most values are on one side and a long tail stretches out on the other. You get heavy tails where extreme values are much more common than the normal model would suggest. You see clear outliers that sit far away from the bulk of the data, and often you only have small samples, so the shape of the distribution is uncertain and unstable. In all of these situations, blindly applying the 6-8-9-5-9-9-9-7 rule is dangerous because it only holds under true normality. This is why we need a different kind of tool, one that makes almost no assumptions about the shape of the distribution but still gives us guaranteed probability bounds. That's exactly where Chebyshev's inequality comes in. On this slide, we start building an intuition for Chebyshev's inequality. Look at the generic distribution on the screen. It's not a perfect bell curve. It's just some data with a mean, marked here as mu, and a standard deviation sigma. Chebyshev's inequality tells us something very general about this picture, no matter what the exact shape of the distribution is, as long as the mean and variance exist. Most of the values must lie within some number k of standard deviations from that mean. The central shaded band you see between mu minus k sigma and mu plus k sigma represents that interval. Chebyshev guarantees a minimum fraction of the data inside this band. The tails outside that band can be too large. This is why Chebyshev is so powerful. It works for almost any distribution you might encounter in real data. Now that we've built some intuition, let's state Chebyshev's inequality formally, as you see on the slide. Here, x is our random variable. It could be daily sales, transaction amount, model error, anything. The symbol mu is the mean of x, its long-run average. The symbol sigma is the standard deviation, which measures how spread out x is around that mean. And k is just a positive number bigger than 1, telling us how many standard deviations away from the mean we are looking. The first line says the probability that x is at least k standard deviations away from the mean in either direction is at most 1 over k squared. In other words, being far from the mean is rare, and its probability has this hard upper bound. The second equivalent line flips the perspective. The probability that x stays within k standard deviations of the mean is at least 1 minus 1 over k squared. So it's a guaranteed minimum probability of being close to the mean. And remember the side note, this works for any distribution with finite variance. Now let's turn those formulas into concrete numbers. On the left you see what Chebyshev guarantees for different values of k. For k equals sine 2, it says at least 75% of all observations must lie within 2 standard deviations of the mean. For k equals sine 3, the guarantee becomes at least about 88.9% within 3 standard deviations. For k equals sine 4, at least 93.75% within 4 standard deviations. These are worst-case minimum guarantees. Real data often puts much more mass near the center than this, but it can never put less as long as the variance is finite. On the right, you see a comparison for two standard deviations, the normal 95% rule versus Chebyshev's 75% guarantee. The normal rule is tighter, but it is only valid if the data are actually close to normal. Chebyshev's bound is more conservative, but it is universally valid, no matter how skewed, heavy-tailed, or irregular your distribution is. On this slide, we are finally putting Chebyshev to work on a practical business problem. Imagine you're the data analyst for a retail company. You've estimated that average daily sales are 1,000 units, with a standard deviation of 200 units. Using Chebyshev with k equal to 3, you can say at least about 88.9% of days will have sales between 400 and 1,600 units. That range is what you see as the shaded band around the mean on the chart, from mean minus 3 standard deviations to mean plus 3 standard deviations. Most of the line stays inside this band with only a few days falling outside. The key point is that this statement does not rely on sales being normally distributed. Even if the distribution is skewed or irregular, as long as the variance is finite, this is a valid guaranteed lower bound. You can repeat exactly the same logic for returns, transaction amounts, daily profit, or operational metrics, and communicate to managers in plain language. With at least 89% probability, this KPI will stay between X and Y without ever assuming a bell curve. Now let's see how Chebyshev helps with outliers. On this slide you see a distribution with most observations concentrated around the mean, and a few points far out in the tails, beyond the band that represents several standard deviations. Chebyshev's inequality tells you how rare those extreme values should be if the data really follow the estimated mean and standard deviation. For a distance of k standard deviations from the mean, at most 1 over k squared of all observations can lie that far out. For example, if you choose k equals 4, then at most 1/16, about 6.25% of your data should fall beyond plus or minus 4 standard deviations. If you look at your plot and you see many more points outside that band, that's a signal. Maybe you have heavy tails, data quality problems, or genuinely unusual events worth investigating. Use these as a diagnostic guide to flag potential outliers and to ask questions. It is not an automatic rule for removing data. Now let's connect Chebyshev's inequality directly to machine learning and analytics. On this slide you see a simple pipeline, features flow into a model, which produces predictions. Next to it, we are looking at the distribution of the model's prediction errors. If you can estimate the mean and standard deviation of these errors, Chebyshev lets you state conservative guarantees without assuming the residuals are normal or nicely behaved. For example, you can say, given our current error mean and standard deviation, at least a certain percentage of predictions will fall within this error band. That shaded central region on the error chart represents this guaranteed band, while the red tail points show the small fraction of large errors that Chebyshev allows. This is extremely valuable in risk-averse domains like finance, operations, or healthcare, where you want worst-case style assurances, bounds that hold even if the true error distribution is skewed, heavy-tailed, or just unknown. You can use Chebyshev for error analysis to provide minimum performance guarantees and to stress test models under conservative model-agnostic assumptions. Chebyshev's inequality is powerful exactly because it assumes so little about your data, but that also makes it conservative. Use it mainly in the general case on the left, when you don't really know the distribution, when the shape is clearly non-normal, or when you only have a small sample and the histogram looks unstable. In these situations, you still want a hard guarantee based only on the mean and the standard deviation, and Chebyshev gives you that. But remember the bullets on the slide, it requires finite variance and the bounds it produces can be very loose. That's why you should treat Chebyshev as a safety net, not as your final model. Always combine it with exploratory data analysis and domain knowledge. Look at distributions, time plots, and context, and then ask whether more specific models make sense. In the special normal case, on the right, when normality is a reasonable assumption, classic normal-based rules give you much tighter, more informative bounds than Chebyshev. Let's wrap up with the key ideas from this video. Chebyshev's inequality gives you conservative but universal probability bounds. As long as your data have a well-defined mean and standard deviation, you can guarantee that most observations lie within a chosen number of standard deviations from the mean without assuming a normal distribution. This makes it a practical tool to interpret variability, check for potential outliers, and support robust risk-aware decisions when normality is doubtful or clearly violated. If you'd like to move from theory to practice, I invite you to download the free sample of my book, Statistics with Python, 100 solved exercises for data analysis. Inside you'll find step-by-step Python exercises on probability, hypothesis testing, correlation, regression, and general statistical analysis, all designed for real-world data work. If you found this video helpful, please like it, subscribe to the channel, and share it with colleagues or friends who might benefit. Thanks for watching, and see you in the next video.